when we actually go back to this assumption that today is our point of reference so that that n is 0, then of course this becomes a lot more manageable, because you can see t is equal to 0, then this payment is 0. When t is equal to 1, this payment was 100, and it was 10%. The big N was 4, the little t was 1, and so you're basically compounding that payment in the first period. You're compounding it 3 periods. And if you look back on your screen, you'll see that's exactly what we did. Time was equal to 2. We still had $100, but in that case it was 4 minus 2, so you had 2 periods. So this formula, if you look at it, corresponds exactly what we did and what you understood when we took the $100 annuity and compounded each of the components to the 4th period. It turns out that this formula with the summations, which looks a little bit hairy, can actually be simplified if the annuity is uniform. So if we have this series of payments that are the same quantities, we call that uniform. And basically what that's saying, if the amount in the first period is the same as the second period, is the same in the nth period, since they're the same, we don't have to subscript them, we can just call them an annuity. And in this particular problem, notice that that's exactly the case, that each of those sums of money are 100. So it's a uniform annuity, which means these are all the same. So we can say that A is equal to 100, okay, instead of subscripting it. Under that scenario, we can simplify this formula. Okay, so what we're going to present now is the formula for the future value of a uniform series of payments, a uniform annuity. Okay, to keep this in context, you have one formula, which is the future value of a single sum of money. You have the present value of a single sum of money. Now we're presenting the future value of a uniform annuity. So this is your third formula, the third out of 4 that you will live with for this semester. If you recall, this was the formula that we could use for valuing a future value of a series of payments. Now in this particular case, PT has been replaced with this A, which represents the annuity. Now, using the arithmetic of series, this summation disappears with this formula. I'm asking you now to have faith that if you use the arithmetic of the series, you can get rid of that summation, and you have then the annuity multiplied by 1 plus the rate to the nth power minus 1 all over r. To prevent having to carry these numerical symbols, okay, wherever we go, we're going to take what's in brackets and just define that as the USFV, the Uniform Series Future Value Factor, and we subscripted R and N. R for the interest rate, uppercase N for the number of periods. But just for those of you that want to remember or program this into your calculators, from now on I'm going to show the USFV factor instead of the 1 plus r to the n minus 1 all over r. But you can dog-ear that in your textbook or in your notes if you want to go back and see the actual arithmetic. Okay, now let's go back to this problem. We have our timeline. We have a $100 annuity paid at the end of each of the next 4 years, drawn 10%, and we want to know its value in 4 years. Now again, we have to use the logic to figure out which formula to use. In this particular case, is there a series of payments? The answer is yes. Is it uniform, meaning is it the same quantity in each period? Yes. So immediately we know that we're going to use a uniform annuity formula and not the single sum formula. And because we want to know the future value, so we want the future value to be on the left-hand side of the equation because that's the unknown, that's what we want to know. We are going to use the future value of a uniform annuity. Okay, now that looks simple, but when you get a problem that's got a lot of wording and verbiage in it, you have to be able to think through the logic, put it into the timeline, and then look at the timeline. Otherwise, you end up using linear inches to solve your problem instead of the area or volume. Okay, so in this particular case, we set it up and we're going to solve it on our calculators. You see that the annuity is a $100 annuity. It's uniform, and it fits into our future value uniform annuity. The interest rate is 10%. Notice that the number of periods, end of period cash flows, these are end of period, are 4. So we take the 4, this 4N, we have a 10I. Notice in this case, do we have a present value? The answer is no, so we have to zero out present value on our calculators, and that's important, and I stress that because if you don't, there's memory in your calculator and you're not going to get the right answer. You've got to zero it out in this case. And your payment we've already determined was 100, and so we calculate the future value, and there shouldn't be any surprise that the answer is $464.10, which is exactly what we obtained when we did it the long way by treating each cash flow separately and compounding them to the future. So there's at least some evidence that the formula that I presented and is embedded in your calculators works. Excel can also handle these types of problems when it's uniform. We have the $100 annuity, and this is the formula to solve that right here. We put it right there in that cell. You can see the formula down here in blue. We have equals the future value, 10%, 4 periods, $100 payment. We zero out the future value. The type is 0, or it could be left off, representing that these are at the end of period cash flows. And of course it gives us the same answer as our calculator. Has to, because it's using the same formula. Now that we have this formula, we can use it in what's called a sinking fund, meaning where we are setting aside sums of money over a period of time to obtain or achieve some level of money. So to calculate this sinking fund, we're going to calculate this uniform annuity, this A, which we defined in the previous examples, that is equivalent to a single sum of money in the future, this VN, at time N given an interest rate. So if we know the future value of money that we want, we know the number of periods by which we have that sum of money, we know the interest rate, we want to know how much money then do we have to set aside. We can do this in planned capital purchases. For example, if you are into real estate and you want to buy a rental property, do you have to replace the roof every year? Do you have to replace the air conditioning every year? And if you're lucky, do you have to replace the carpet every year? No, but there are some statistical periods of time where you expect those things to happen. And what happens if you don't save money or set aside money for those repairs? You either have to borrow it, or you have to take money out of your savings account or out of your other planned purchases. So in farming, you're going to use a tractor forever. Sometimes it seems that way, but at some point you need to replace that. And you can set up a sinking fund, or you can set aside money so that when you need to replace it, you have at least enough for the down payment, if not more. And of course, for retirement fund, we've talked about these in the context of single sums of money, but it's actually a better concept to be putting aside money on a monthly basis to plan for your retirement. We also hopefully made a point that it makes a big difference if you start planning now for 40 years as opposed to putting that money aside when you have 10 or 15 years left before you plan on retiring. To look at this, remember we said that we knew the amount of money that we wanted in some future point in time that we're designating as this uppercase N. We know the interest rate that we can achieve. We've already said that we know the period of time. What we don't know is this A. So algebraically, we just divide both sides of the equation by the USFV factor. So that's how we would do it algebraically. Of course, your calculator is already programmed to do that. Here's an example for a planned capital purchase. Suppose you plan to replace a tractor in 5 years, and it will cost you $55,000. How much money would you need to put in your savings account at the end of the next 5 years to achieve this goal if the interest rate is 7%? Okay, we get twisted again in the vocabulary here. So let's pull out the numbers and put it into our timeline so we can visually see what we're asking. We're saying that we want to buy a tractor for $55,000 in 5 years. We also pull out of that problem that we can earn 7% on our money. The question is how much money do we need to put in our bank account at the end of the next 5 years? Now, as a formality, these little dots are just, as you already know, represent continuations. And certainly in your homeworks or your problems where that becomes useful, feel free to use those dots. It just means it's repetition. Now, in this particular case, which formula do we use? Again, is this a uniform annuity? Yes, it's a uniform annuity. Do we know the future value? So it makes sense then that we're going to use the future value of a uniform annuity. Again, the logic, so we know which is the appropriate formula to use. As I mentioned before, this problem we can solve algebraically because we could divide the 55,000 by the USFV factor. Or we can rely on our calculator, and I suggest that if you have your calculator, you pull it out. Okay, we see that the number of periods is 5. So we put 5 in. The interest rate is 7%, so we put 7i. Again, if you look, we have no present value, so we zero it out. We have a $55,000 is our future value. We plug $55,000 into future value. Then we compute the payment, and the payment comes out to $9,563.98. What that says is if we earn 7% on our money, if we put $9,563.98 from our earnings, okay, that retained earnings that we talked about, if we take that and earmark it into a savings account, and every year, okay, we take earnings and put it back into that, which is a good idea because it's covering our depreciation, then at the end of the 5th year, we have the $55,000 that we need to buy the new tractor. You might say, so what? Every one of you are going to be in some situation where you are going to have to face some expenditure in the future. I'll give you a classic example right now. When you want to go out and buy that $18,000 truck, instead of having to go hat in hand to your banker and ask for a loan on that truck, drive the vehicle that you've got now for 3 or 4 years and set aside the amount of money that you need monthly instead of the mortgage payment on the new truck, put it in a bank until you accumulate the amount of money that you can pay cash. That way you're saving the interest instead of paying the banker. From a personal standpoint, I don't borrow for cars. I pay cash. And each month I have a account that's set aside where I put in a sinking fund. Instead of paying the bank a car payment, I pay myself a payment for the vehicles. So that when we get ready for a new vehicle, I say, we've got this much money in the sinking fund, we can buy this type of a vehicle. What I'm trying to tell you, this is something that you should be looking at. And if that means having to drive your old clunker for a few more years until you can start getting into that cycle, break out of the cycle, borrowing till you need a new car, almost paid off, then borrow again. Okay, get on the other side so that you're earning the interest instead of paying the interest. And this allows you to do that, whether it's a tractor in your agriculture or combine, or whether it's a new horse. Whatever those things are depreciating, you can set up this sinking fund, and now you have a formula that allows you to do that. You can figure out what it is, how much you have to set aside each month. Actually, I'd encourage you to think about that a little bit in your personal finance. Okay, now in Excel you can do the same thing for these trying to calculate the annuity. We can use this formula where you're basically saying equals the payment. And you have the rate, the number of periods, the present value, the future value, and this type again represents whether it's end of period or beginning period cash flow. And for examples, we're using end of period cash flow. So in this particular problem, you would put equal this PMT for payment. Then you have to put in your arguments. You would have put a 7% interest, 5 periods. The present value, we zeroed it out just like we did on our calculator. The $55,000 represents the future value. I omitted the 0 because that implied it's the end of period of cash flows. And sure enough, it gives us the same answer as our calculator.